Hey everyone, my name is Diana Chan Morgan and I run all things community here at deeplearning.ai. Today we are so lucky to have some special guests from Galileo to walk us through LLM hallucinations with the metrics first evaluation framework. For everyone that is watching, the session will be recorded and available for replay after the fact. But if you have any questions, please check the link in the chat in our Slido, which you'll be able to vote on questions the speakers will answer at the end. We're also very fortunate to have some of their developer evangelists, Setu and Jonathan, in the chat as well. So if you have any additional questions, feel free to ask any questions there as well. So for today's event and workshop, what you can definitely expect is a deep dive into research-backed metrics to evaluate the quality of the inputs, whether that's data quality, RAG context quality, and outputs, whether that's hallucinations within the context of LLM-powered applications. We'll also be talking about an evaluation and experimentation framework, while prompt engineering with RAG, as well as fine-tuning with your own data. And of course, we'll have a really well-led demo by our speakers today that will definitely help you be able to implement this on your own. This event is also inspired by deeplearning.ai's generative AI short courses, created in collaboration with AI companies across the globe. Our courses will help you learn new skills, tools, and concepts efficiently within 1 hour. And now to introduce some of our speakers, our first speaker is Vikram Chatterjee. Vikram is the co-founder and CEO at Galileo, an evaluation, experimentation, and observability platform for large language models. Prior to Galileo, Vikram led product management at Google AI, where his team leveraged language models to build models for the Fortune 2000 across retail, financial services, healthcare, and contact centers. He also led product for Google Pay in India, taking it from 0 to 100 million monthly users, the most downloaded fintech app globally. He is also one of the early members of the Android OS team and believes generative AI is ushering in a similar technological wave to mobile. Hey, Vikram.
Hi, Diana. Thank you so much for having us.
Of course. And to introduce our second speaker, this is Atendrio Sanyal. Atendrio is the co-founder and CTO at Galileo. And prior to Galileo, Atendrio was an engineering leader at Uber AI, responsible for various machine learning initiatives at the company. He was one of the architects of the world's first feature store, Michelangelo, and early engineers on Siri at Apple, building their foundational technology and infrastructure that democratized machine learning at Apple. We are so lucky to have them all here today. And without further ado, let's definitely get started. So, Vikram, do you want to take it away?
Sounds good, Diana. Thank you so much for that introduction. And also, welcome everybody. Really excited to have everyone here for the workshop. It's going to be hopefully an exciting one, but also something that you can take a lot of really interesting nuggets away from. So the topic of today's workshop is something which is super close to our hearts and something which is very top of mind, I feel like, for the industry as well, as we all grapple with large language models. It's about how do you mitigate LLM hallucinations, but how do you do that with a metrics first evaluation framework? So to kick things off, I'm going to start with something with an agenda about what we'll be covering today. The first thing we'll talk about is the need for LLM experimentation and evaluation frameworks. I feel like we're all hitting these brick walls, but and quickly realizing that there's a need for this. We'll go over exactly why and what that means. Second, we'll talk about different kinds of evaluation methods and when to use them. And then we'll further, number 3, dive into emerging hallucination detection metrics that are coming out in the ecosystem, but also how we can push the envelope further and build them up specifically for the LLM era. And last, we'll go through a demo to walk through how you can bring this all together and have this experimentation be done in the right way, but also with the right kind of metrics in place. And we'll walk you through a simple app that we've built out and how you could mitigate hallucinations, whether you're using RAG or whether you're fine-tuning with your own data. To start with, I'm going to start with a 100,000-foot view, right? Like when you think about LLMs, we have you have a lot of inputs that go into the LLMs, and then you have the outputs. This is classic machine learning. You also have a feedback loop, right, from the outputs which go back into the inputs. That's basically it. It should be simple, but it's not, because as soon as you start dabbling with large language models, you immediately realize that there's an explosion on both sides, the inputs and the outputs. Also, on the input side, for instance, as soon as you start working with large language models, you realize that, wait, I have a bunch of different large language model parameters that I need to tweak, whether it's the temperature or any such thing. There's a whole host of them that you need to tweak. There's the prompt template that we all know if you tweak it just the slightest bit leads to all sorts of different results on the other side. Constant experimentation happening there. There's chains that you can bring together, create agents, and have multi-agents. It becomes super complex super quickly. You have RAG in the mix with different RAG parameters, all the context data that you need to add into the vector store, whether it's good, is it bad. Then start thinking about fine-tuning. You start thinking about the quality of the data that you're putting in. Do you have sufficient data in the first place? And so much more. So it just blows up. The inputs themselves are mind-boggling. When it comes to the outputs, it depends on your use case. Now you might have a text summarization use case, or text generation, or chat, etc., or question and answering, or code generation, and so many more. And for each one of these different kinds of outputs that you're expecting from the large language model, right, the way you evaluate them has to be different. You can't be evaluating turn by turn chat the same way you're evaluating text generation. It just doesn't work that way. So the complexities just exponentially increase. And so in order to solve for this, what we really need to think a lot more about is on the input side, right? How do you iteratively experiment? And today, when you look at how people experimenting in our community, it's highly manual. It's mostly still being done in notebooks, or we've seen people use Excel sheets and Notion documents, all sorts of stuff. And when you think about it, that's not how data science should work. You should not be experimenting with all of these different ingredients, which are essentially your IP in Notion documents or Google Docs. On the output side, the output evaluation has now reduced to essentially eyeballing. With erstwhile natural language processing, we at least had our friendly neighborhood F1 score, which could help us be the North Star for are you moving the right direction or not. It's debatable how accurate and good it is, but at least it was an evaluation metric that we all gravitated around. With LLMs, you don't have that. So we're seeing companies at the highest level of sophistication still just eyeballing the outputs with large number of humans in the loop, which obviously increases the amount of bias and is far from accurate, right? So when we think about this, and we thought about this at Galileo, we've built out what we call the Galileo LLM Studio, which is essentially an experimentation, evaluation, and real-time observability bench for any data science team or developer that's working with large language models. The way we think of it as from a framework perspective is there are three parts to this, right? And three modules as a part of the product as well. The first one is called prompt, which is all about accelerating prompt engineering. So when it comes to the inputs from your vector store, or your prompt template, or your LLM parameters, how do you experiment across all of that to make sure you're working towards the right set of inputs? The second one becomes fine-tuned, where you're fine-tuning your large language model. You have to make sure that you're doing that with the highest quality data, and you're constantly moving in the right direction. It's super important to experiment and be iterative in this process. And the third one is monitoring, because you can create all the guardrails you want before production. We all know when you put a model in production, given its probabilistic nature, things can go wrong. You have to immediately know whether you need to tweak your prompt or you need to add additional data for fine-tuning. And all of this together is essentially how we think about experimentation and observability. And so we strongly urge anybody, whether you're using Galileo or not, to be thinking about experimentation and observability constantly across all three of these big pieces. Apart from this, experimentation is meaningless without metrics, right? Without good metrics. That's how all fields of science work. And so for us, since the very beginning of day one of Galileo 2.5 years ago, we were all about language models and all about building metrics for evaluating large language models. We built out what we call the Guardrails metric store, which has a bunch of research-backed metrics, which we have designed, a lot of them within Galileo, but a lot of them have been built on top of open source metrics as well, so that you can make sure that you can reduce hallucinations and build trustworthy LLM applications. But these guardrail metrics are super important from an output evaluation perspective. So let's dive deeper into that for a second. And if you double click on output evaluation metrics, and in general, as you think about building large language models based applications, when you're thinking about these evaluation metrics, we urge you to think of it in three different ways. There's the output quality metrics, there's customized metrics for your specific product and business use case, and then there's the output hallucination metrics. So what do I mean by that? First of all, for the quality metrics, there's a whole host of them. For instance, tone of voice. Is your output of your chat product getting, is the tone angry? Is it happy? Is it sad? What do you want it to be? Is there any PII presence? For a lot of regulated industries, that's super important to be completely on top of. Is there toxicity? Is there any kind of bias that's being spewed? Is there hatefulness or sexism or many such other kinds of quality attributes of the output that you need to be very on top of? The second kind of metric is, we call it the custom metric. Like, for instance, AI policy adherence. There's the EU AI Act coming up and some other data acts in the US itself. You have to be adherent for that if you want to launch credible models. Compliance adherence or business metrics adherence as well, and many other such customized metrics that you need to think about. The last one is called we call it the output hallucination metrics, right? This is basically how do you know whether the LLM's output is correct or not? And this is where there's a huge bottleneck today, right? How can you consistently and accurately measure the correctness of the LLM output? When we think of this, we divide that into two large buckets. One is for any team that's working with RAG workflows or non-RAG workflows, and that non-RAG includes fine tuning, or you can combine fine tuning with RAG, but essentially think of it as, do you have context involved or do you not have context involved? And go deeper into this a little bit more because this warrants its own discussion. So what we'll do next is go deeper on the LLM output hallucination metrics and the different categories, and some proposals around what you could use for detecting hallucinations with your LLMs. Atin, do you want to take it from here?
Yeah, thank you. So yeah, we'll dive a little bit deeper into the third category of output metrics, which Vikram was talking about, essentially hallucinations and the existing methods that help quantify some of them. Just before we dive a bit deeper, I just want to set context on what we mean when we say hallucinations. Essentially, it refers to instances where the LLM output might sound coherent or plausible, but has like logical fallacies in them, or there's factual validity issues, as well as if there's context, the LLM does not adhere to the context or the instructions which are provided in the input. And then there's many reasons why hallucinations occur, which is a bit beyond the scope of this talk. There's limitations in training data, model quality, etc. And there's a few methods which have been explored in the recent literature to quantify modern hallucinations, but they kind of broadly fall into three categories of techniques. The first one is essentially based on measuring the amount of overlap between the output of the LLM and a reference ground truth. Now, of course, this is only possible if there is a ground truth or a reference data point in existence. And a lot of the use cases around LLMs typically work without a reference these days. So in those cases, this sort of n-gram matching category does not apply. The second technique is based on asking an LLM if it thinks whether an input completion pair has hallucinated or not. Now, this is the basis for a lot of the more widely adopted modern techniques to detect hallucinations. And of course, it has certain merits, but there's many limitations around that, which I'll get into. And the third category is essentially, most LLMs are basically token spewing machines, and each token has a probability distribution amongst a vocabulary. So when you gauge into the statistical properties of these probability distributions, you can get some intuitive sense around whether the model got confused and whether it hallucinated. So those are the high-level intuitions, and I'll get into each of them one by one. So the first one, a popular suite of metrics which leverage the first technique include metrics like blue and rouge scores, which are essentially measuring n-gram overlap. So they look at phrases and they essentially try to see whether how much overlap is there between the output of the LLM and a reference ground truth, and that gets converted into a 0 to 1 score. There's also Meteor, which is kind of a different version of the same idea, which takes into account things like word order and synonyms. So it bolsters the Blue and Rouge scores a little bit. But they're all based on this underlying principle that measurements of similarity to existing ground truth can give you some semblance of hallucinations. Now, of course, from the definition, there's decent amount of applicability, especially in historic use cases. These kind of metrics were typically used in translation quality, not just in language technologies, but also in speech-based systems as well. But you can see that there's a lot of limitations in this kind of an approach. For one, it requires the presence of a ground truth and reference data, which is typically not common as language tech has been adopted more and more. These kind of metrics, they fail to adapt to stylistic changes, where words might be different, but the overall meaning might be the same. So it can lead to a lot of false positives and false negatives. And essentially, to summarize, comparing words and tokens to measure hallucinations is overall not a great idea for most part. The second category of technique is it revolves around the idea of asking a GPT model or some state-of-the-art LLM if it thinks whether the pair of the input and the output hallucinated. And there's many ways to go about this. Of course, you can directly ask an LLM, hey, do you think this is hallucinating? Or you can do multiple reruns and get multiple generations and check consistency across them. This kind of category broadly falls under the self-check method, which was recently published a few months ago. And it certainly has its merits. The foremost being it's not restricted by a ground truth. And it's kind of designed to capture some of these higher order fallacies, which means that the applicability is fairly broad. And this kind of a technique can detect more higher order hallucinations. But again, it is very restricted. Vikram, do you want to move to the next?
Yep.
Yeah, so it's fairly restricted. Number one being that it's a black box technique, right? You're asking a magic ball if something's hallucinated. It will fail to capture reasons behind false positives and false negatives. It can be prohibitively expensive if you use more state-of-the-art models like GPT-4 to give you whether something's hallucinated or not. And more importantly, it lacks the explainability, which is critical for users if you want to take corrective action. As you'll see, there's many different kinds of hallucinations, open domain, closed domain, and taking the right action, it relies heavily on being able to explain what the hallucination is about. And the third and final category of existing metrics to measure hallucinations is based on the doing math and probability statistics on top of the probabilities. You essentially look at the token level confidence of these models as it's constructing the output. And the intuition here is that this kind of measure gives you a sense of the model's uncertainty in its own response and may suggest some semblance of hallucinations. But from our various in-depth experiments over the last year, it has shown that while techniques like these are great secondary signals of model confusion, they are essentially a bit too granular. Vikram, if you want to move to the a bit too granular in its ability to capture higher order signals of hallucination. And another restriction here is that a lot of LLM APIs typically don't return you log probs. And in those cases, techniques like these kind of become a little restrictive. So we've talked about the three broad categories of metrics which are today used for hallucinations. And there's many experiments which we've done internally to identify issues in these existing metrics. And we essentially figured that there is a need for a new technique which not only takes some of the better principles of the techniques which I spoke about, but also leverages these distinctive powers of these new LLMs, like their ability to respond to chain of thought prompting, and use that to create a new category of metrics, which number one is more accurate in its results. And number two, it's applicable to real world scenarios. It scales to different kinds of tasks. And finally, it is cheap to compute. And it should work at low latency because we are all building practical metric systems here. So with that, we created a new technique to identify hallucinations. And this technique is called Chainpole. And Chainpole essentially is a high efficacy method to detect hallucinations. Vikram, move to the next one.
Yeah.
And here in Chainpole, we break down detecting hallucinations into two phases. The first phase is called chaining. And in chaining, we essentially use a very detailed chain of thought prompt to make a secondary LLM request and gauge if it can reasonably sort of break down the reasoning behind the completion that it just made. And then we collect the chain of thought reasoning. Think of it as we structure it down into a specific schema. And then we do what we call is polling. And polling is essentially this ensembling technique where we try to gather evidence of fallacies in the chain of thought through voting. And voting is a common technique used in machine learning, whether it's like classic models like random forest. Ensembling is a general way to get really good results. And think of it as though it's, there's domain experts in the room and you're kind of getting structured schematic responses from each of them. And then you're trying to make a claim of whether the model hallucinated or not. So here's a high-level flow of Chainpole. The user makes a query to the LLM, and the LLM responds with a completion. Then what we do is we check if the LLM also provided a probability distribution of response tokens. This kind of goes back to the third category where these log probs act as a good secondary signal to hallucination. So if the output has no log probs, we employ a special generation prompt to match the original log probs in theory. And then we send the newly generated log probs along with the original prompt and response to a chain of thought module. We call it the detailed chain of thought module, and that's basically our core ensembling algorithm. And behind the scenes, we are using batch inferencing to be able to essentially reduce the number of model calls we make to just one. And the key learning behind this has been that chain of thought, the depth of the chain of thought prompt makes a significant difference in the quality of the hallucination detection. And the more detailed and more organized the prompt is, the smaller the model that you can use to generate accurate scores. In fact, you'll see in a couple of slides ahead that we used models like DaVinci, which are at this point fairly dated, to be able to achieve over 23% improvements in compared to the next best hallucination technique around self-checks. And then we take the output of the ensembling module and create like this aggregate score along with an explanation using the chain of thought process, pass it to this cleaning and optimization module, and then finally give a user a normalized score of hallucination along with a clear step-by-step explanation of what may have gone wrong. So just to highlight a super high-level result on all our experiments on all data sets, Chainpole here significantly performed better than the next best, which is a self-check BERT technique, which was launched this year in July in the UK. And you can see how much better it is compared to some of the more common metrics which are used today to detect modern hallucinations. There's many advantages to Chainpole. Number one is that it is designed to be as accurate as possible. Like the whole motivation of the ensembling and the chaining is to increase the accuracy across a breadth of possible real-world tasks. Now, the whole motivation behind this is that our metrics should apply to real-world scenarios and not just stick to like academic data sets or textbookish examples. The second is that explainability is key. Like I mentioned, like hallucinations in modern LLMs are very, very nuanced. Sometimes it spews opinions. So there's the devil is in the detail of what's right or wrong. And these LLMs essentially act very similar to humans sometimes. So it's very important to give you feedback, which is understandable by a human being to be able to take action and next steps. There's a need for low latency as well. There's a significant amount of engineering our team has done to make sure that the algorithm itself works in parallel and the different computations are asynchronous. We want to minimize API calls as well and do batch inferencing to finally reduce cost, because cost is a very big factor here. So This is Chainpole in summary. This is the method, but the outcome of the Chainpole method are two metrics, which we apply to the two broad workflows we observe in LLMs. The first metric is correctness, which applies to sort of these open-ended, open domain use cases where the user essentially passes a query with or without context, and the correctness metric looks at the consistency in the reasoning behind the LLM's completion and how correct the output model can be. The other is the fact that the Chainpole is also correctness in particular is kind of agnostic to whether the context was passed in or not. The second metric is context adherence, which essentially measures how much grounded the LLM output was in the context which was provided. It is very helpful in RAG workflows where you essentially have context in the form of documents which are fetched from the vector store. So I'll show you a couple of simple examples of correctness and context adherence. In the next slide here, you can see this is a very simple example of correctness in action where the user essentially asked a factual question: when and where was Abraham Lincoln born? And the output of the LLM was Abraham Lincoln was born on this date near Laron County, Kentucky. And in this case, the model made a token level mistake. It was very clear. And the algorithm detected the correctness was low. And it gave an explanation that Abraham Lincoln was born in LaRue County and not Laron County. The next example is a more complex example, which really shines a light on the efficacy of chaining on ensembling. This is an RAG use case where the prompt specifies a topic, or rather the prompt asks the LLM to describe the topic that's in the documents which are passed as context. And if you look at the output of the LLM here, you will see that on the onset, it seems very coherent. It says the study is described as a descriptive study of hospitalized cases of influenza in the last 5 seasons. On the onset, it might look correct, but if you really dive deep, the devil is in the detail here. The algorithm found that almost nothing in the output was really related to the context at all, and the adherence score was low here. And you can see that here it is going one level deeper, where it's highlighting where the LLM may have picked up its reasoning from and how it got it wrong, and point to specific areas of the document where the mistake might have been. So here, this is you can see overall the experience is kind of like asking this expert, and you're able to pinpoint to specific areas of the document where the model might be hallucinating. Quick shining a light on the results here. The mean ROC scores for both open and closed domain use cases. You can see that there's significant improvements in the Chainpole methodology compared to self-check and some of these other metrics used like geval, as well as using entropy and GPT score. And then finally, one extra set of results before we dive into the demo. This is showing you the 4 most challenging data sets that we used in our experiments across 4 different tasks. And you can see that we got, just to shine a light on the experimental process, we got domain experts from the world over to annotate thousands and thousands of data points as hallucinated or not. And in the results here, you can see the 85% AUC score on Trivia QA essentially shows that Chainpole came closest to matching a human expert to determining hallucinations. With that, we'll dive into a demo.
Thanks, Atin. All right, it's demo time. Hopefully that was educational, that was interesting. Please keep the questions flowing in. More than happy to take them at the end. We'll try to leave around at least 5 to 10 minutes in the end for question and answers. So the demo is going to be twofold. The first one is going to be about just prompt engineering with the vector store, so the classic RAG use case, and how you can be better about experimentation with the inputs using some of these metrics that Atin talked about. And the second one is going to be about fine-tuning with your own data. the use case for the first part, which is prompt engineering with RAG, is going to be one where I'll walk you through how we built out a simple Q&A app for kids. So, a child can come in and ask a question, and the LLM gives a response. The ingredients were a vector store with thousands of different Wikipedia articles for context, a data set of prompts, and a set of LLMs that we were using to experiment with. We used some of the closed source LLMs as well as some open source LLMs just to see, what combination of prompts and LLMs, etc., would work the best. So for this first demo, typically as a data scientist, we like to work in notebooks, in Python notebooks, and so that's typically where we've been doing our prompt engineering. You could also do this in an IDE, for instance, but in this demo, what I'll walk through is in a notebook as you're doing the prompt engineering, how you could use Galileo in this case to be able to experiment faster. But the takeaways from here, I feel like, go far beyond Galileo. It's basically we're trying to talk through how you can think about experimentation and how you can think about applying the different metrics at different pieces of the application. So to start out with, to build out this Q&A app for kids, I'm going to go into my notebook. I'm going to pip install, this is my notebook. So I'm going to pip install prompt quality, which is Galileo's Python client for prompt engineering. Once I do that, I just quickly load my prompts like I usually do. In this case, what I did was we just used the Stanford Q&A dataset, which is a fairly popular dataset. It's called Squad. So literally just use that. That data set has a bunch of context that provides and a bunch of questions, which are the prompts, right? Once I'm done with this, I get the relevant passages from Pinecone the way I usually do with these vector stores. I throw in thousands of different Wikipedia articles in here. Once I'm done with that, I start creating a prompt run with Galileo. So this is typically where you're starting to think about what should the prompt template be that I leverage. So in this case, we started with something simple. We just said, you are a helpful assistant given the following context, answer the question, provide an accurate and factual response. I get the context from my vector store, and I get the question, which is the different prompts that I added above in the data set from Squad. Now, once I'm done with this, I log in, and once I'm done with that, I add the metrics that I want to see. Right now, remember the guardrail metrics we talked about and that Atin mentioned as well. So the question becomes, for your use case, for your product, what are the different metrics that you want to see? It's important to start considering this before you even start the prompt engineering process. Like, what are the important metrics which are top of mind? So for instance, for us here, because we're using Pinecone, we cared a lot about the adherence of the output to the context that was provided in the vector store. So context adherence, the metric that Atin talked about, is one that we want to see what that looks like. Ideally, this should be a 1, which means it's perfectly within context, every single output. Context relevance, which is the relevance of the input to the context. Correctness, which is this is the level of kind of detects the level of confusion that the model was having as it was coming up with a response, which Atin mentioned, based on our Chainpole technique. Also, we are curious about latency and also sexism. So we want to avoid any such thing in the outputs. The other piece here is, because it's a kids app, we want to create some custom metrics. If there are certain words in the model's output, I want that to be flagged so that I can see why those are coming out in the output, right? And in this case, we just added a few words here. We called it the bag of words metric, but because it's Pythonic, you can make this as complex as you want to. So for instance, in some of our other apps, we've introduced complex models around language detection and gender bias detection, etc., and just registered that with Galileo. So in this case, I just say, if any of these words are present, just return a 1, otherwise return a 0. As simple as that. And I register that with our Galileo Python quality, prompt quality Python client. Once that's done, I give this a project name and choose the model I want to use. In this case, I'm going to go with ChatGPT, their 16K token LLM. And that's it. Once I'm done with that, you get a link to the Galileo console. So no more eyeballing inside of your notebook or exporting to an Excel sheet. Click on this link and we'll take you to the run. Now, when I do this, I essentially get to this UI where what I would urge everyone to think about before you start actually going into the details of their responses is you should take a step back and look at the metrics, right? What's the health of your prompt run? So high level, think of it in three different categories. The first one being the output quality, right? That includes the correctness and lower level metrics like blue and rouge. The RAG metrics, like how good was the context that you provided it, and is the output actually adherent to the context or not? As well as, there are often times when you need humans in the loop in this entire process, and it's a good thing to combine automated the whole automated metrics based experimentation with humans at this stage. So human ratings is super important at a per prompt response level. And then our custom metrics, the bag of words that I just added in here. So to start out with, I can see that the average correctness it's not great. It's good. It's 0.8 out of 1, but not great. It's 0.8. Imagine if your F1 score for an NLP model was 0.8 and you can't ship that. It's probably going to be wrong 10 to 20% of the time. That's not great. So I want to look into this more. So why is that happening? Turns out that the context adherence is not great either. It's 0.789. So that should be ideally a 1. That means every single piece of output is adherent within the context. So this is typically how this is how on a high level I can quickly get a sense for how maybe there's something wrong with the groundedness or the context that I provided the model with. So in order to do that, I can start to look at the responses here, and I can see amongst all of these different metrics that I have at my disposal, there are certain things which I might want to look into a little bit more. So for instance, I can see that it says here that for this particular response, you can see that if you look into the context that was provided, it talks about the weather in a certain part of Australia where the average temperature exceeded 32 degrees Celsius in the summer and exceeded 15 degrees Celsius in the winter. And then it talks more about the different parts of the climate in that region. Now, the question here was about what is the median temperature in the winter? And the model's response was median temperature in the winter is about 15 degrees Celsius. Now, when you look here, that's exactly what it says here. It's 15 degrees Celsius in the winter. So now if I'm, as a human evaluator, if I'm rapidly trying to move through this process, I'm just going to mark this as a thumbs up and move on with my life. I'm going to go to the next one after this and the next one after that and start seeing other prompt responses. But because I see that the overall LLM correctness score is 0 and the context adherence score is 0, I'm curious about why that's happening. So if, remember that Atin mentioned that the technique for coming up with context adherence was using a process where we also get a response from a model which gives us its reasoning, which helps a lot with debugging. So instead of trying to wonder why it's a 0, I can just hover on this to get a rationale from the model. It's an expert telling me why the output is not adherent in the context. So if you look at the last few sentences here, let me try to zoom in here if that maybe makes it easier. If you look at the last few sentences here, it says, to confirm whether the median temperature, so it does the context does not provide the mention the median temperature. To confirm whether the median is also 15, we would need additional data. And so therefore the claim made in the response cannot be fully supported by the documents. So it's clear that it's almost like an expert who's read through all the documents that were provided to Pinecone and says that, all right, it looks like what's been given to me from Pinecone is basically the average temperatures here, but what's being asked from me as to give an answer is the median temperature. And I can't do that because without additional information. So that's a good takeaway for me to have as a developer. I might need to add more context around the median temperatures in certain regions. Maybe I'm building out a weather app for kids in this case. And so I could now, based on that information, mark this as a thumbs down and move on to the next prompt. So that's a quick way in which you can, at a per prompt level, at a per response level, try to debug much faster using these metrics that I mentioned before. Now, all of this is for one prompt run. Now, remember, like when you're working with these LLMs, remember how many different kinds of inputs you have to work with. You can have 10 different LLMs. You can have multiple different kinds of LLM parameters. different kinds of prompt template versions. You can't, like, should you be doing this one by one in this manner? We urge you to think differently from that. So one of the techniques that you could use with the prompt quality Python client with Galileo is called prompt sweep, where think of it as throw the kitchen sink into the Python client, right? So in this case, as a developer, I thought to myself, wait, I tried the GPT-16K token model, but let me try TextAvinci 3 as well. Let me also try GPT-4 and see if that one works better or worse than the others. Instead of one template, I actually have many different ideas for templates. So I'm going to add 4 different templates. All of them are just comma separated from each other with slight nuances and differences in them. I also give it again the same project name and add a bunch of different temperatures, in this case, like 1, 0.5, 0.1, so varying degrees of freedom for the model to come up with its responses and execute that. And at the end, I get a quick estimate based on these API calls that it's making and the vector store that we're using, that the total cost is going to be over $36, which is not cheap, but I'm going to still go for it. And at the end, again, I get a link which takes me to, instead of one run, it's going to take me to many different runs. So all of my runs for this project can be seen over here in one go. Now, this can be a lot. You can see all of the different prompt versions that were used. Galileo automatically version controls them for you, so you don't have to worry about that. It gets stored in what we call your overall prompt store, where it's automatically version controlled for you. You can see the different models that we used here, as well as all of the different metrics that came up for that entire run. Now, how do you figure out which is the best one? Again, if you have a metrics-based approach, it becomes super fast to be able to figure out which of these runs is working out the best for the metrics that you care the most about. And even from here, it's always good as a next step to be able to quickly do an ABN comparison between different kinds of models, for instance. So for instance, here I'm going to keep the version exactly the same as a V0, and I'm going to try out maybe different kinds of models. So that's TextAvinci 003, there's the GPT-4 8K token, there's a ChatGPT 16K, and now it's going to be interesting. Like, everything else kept the same. How did these 3 different models behave against each other? And so you can see over here that if I start looking at the different responses that are coming out, I can inspect the output, just eyeball it, but I can also use the LLM uncertainty metric that Galileo provides, which uses the log probabilities that's coming from the model, essentially, to start to see some really interesting trends where even with everything else kept the same, right, you can start to see how the model's responses are dramatically different from each other, which can be a very interesting insight for me as I start thinking about which model to go ahead with based on its latency, based on its cost, based on its output, and potential hallucinations here. So the takeaway from all of this is you should be able to do multiple prompt runs in one go. Use a metrics first approach to be able to figure out which combination works the best. And A/B testing is super important. But there's a need for not doing this in notebooks or Excel sheets. There should be a collaborative environment where you can leverage, and Galileo is one of them. Eventually, if you do all of this, then you can get a much faster way of figuring out, are you moving in the right direction or not, which model is working the best. And oftentimes, building these LLM applications is a team sport, so you need to have multiple creators. In this case, it was just Galileo itself that was creating these runs, but you could have many different people working on these runs at the same time. So all of this is on the prompt engineering side for coming up with the best combination of inputs so that you can build the best version of your application super quickly. Before I go into the fine-tune piece, right? Let's say I do all of this. You want to put this into production now. Now, when you put an app into production, it's a whole different ballgame, like we talked about. You need to have a real-time understanding of where things are going wrong. Which is why so I'm going to walk you through how this looks in Galileo. But again, if you're using any kind of observability solution, you can leverage Galileo's APIs or any of the metrics that we talked about before to be able to power that solution, right? So it becomes really important for you to figure out not just the high-level cost and latency and API failure metrics, super important, but also start to look at whether there was uncertainty, whether the LLM correctness was in a good spot or not. You might have multiple models in your chain, so you should have all of those models being surveyed at the same time. and you can start to also like map that back to business level metrics like user session length, for instance. So as an example, I can see over here that as soon as the factuality or the correctness started to reduce, the user session length starts to reduce as well, which is an interesting insight for me, where I might want to start diving deeper into that and check for what exactly is going on in that particular instance in near real time, right? And look at the specific data that was causing that problem. And when you start looking at the data and start looking again at the factuality that is coming out of this and the explanation from the model for this, you can quickly get a sense for where you need to tweak your prompts. So at that point, you can, instead of looking for the rummaging through for the notebook where you did that, because Galileo has a prompt store behind the scenes, you can just right click and load this in your prompt playground and see how this particular input from the users is doing with your with all of the with the prompt template that you had, and where you might want to tweak it. And we also strongly urge you to tweak your prompts constantly, and then eventually maybe even try to A/B and experiment with different prompt versions, like 10% with prompt version 1, 20% with prompt version 2. That's how software development works as well. And we did that behind the scenes for this application that we were using, that we built out, that's being used by analysts at banks. And what we noticed is some really interesting trends when you do that. We tweaked multiple prompts, and you can start to compare all of them with live traffic to see which one is actually working out the best or not. So that's, rapid experimentation with powerful metrics allows you to be able to figure out which is the best LLM, which is the best prompt version, in using your users as a constant feedback channel. So all of this was to prove that that it's super important to be able to experiment with the inputs, real-time evaluate your outputs, and have feedback loops constantly, so that you are, as a team, constantly moving in the right direction and improving the LLM application. It's a never-ending process of improvement as the world changes. Now, switching gears towards the second part of the demo, where I mentioned that I would talk about fine-tuning as well. It's super important to think about fine-tuning as a pretty cost-effective way of creating LLMs that can be fairly accurate. Now, in order to do this, the big bottleneck does tend to be whether you have the data or not. And if you're using synthetic data, they tend to be low quality. So then again, the problem of data quality becomes really, really important and top of mind. So in this case, for fine-tune, what I'm going to do is the use case is going to be generating headlines for news articles. And the ingredients will include a corpus of news articles to fine-tune the LLM with, right? Fairly simple use case. Now, I fine-tuned this model in my notebook again, added one line of Galileo code. In this case, the Python client is called data quality. And similar user experience in your notebook, you get a link to and you visualize your data on the other side. So if I go to what that looks like, essentially, in the Galileo UI, you get to see all of your data in one place, as well as a bunch of alerts around what was super hard for the model. So this is where there's a metric that our researchers came up with called the data error potential score, which we're happy to share after this workshop, so that you can look into the math and you can also look into how to apply this. But it's been super powerful as a quantifiable way to figure out what data points the model was having a hard time on. Let's dive into that for a second, right? This is about the ground truth. So first, I'm going to talk about how you can inspect the ground truth with the data error potential to find incorrect ground truth. And the second part becomes hallucinations in the output. So for the ground truth, let's say I go to the pre-trained embeddings, and this is for my test set, by the way. Okay, there's also a training set, but I care a lot about my test set being perfect. So here I can see my embeddings colored by that DEP score, or the data error potential score. So immediately I can get a sense for where things might be going right or wrong. Let me remove the low error potential regions here. And I can start clusters forming here. So for instance, there's one over here on the side, which if I make a quick selection of that one, I can see that it's the average DEP is quite high, which is high error potential. So if I look at the table view, I can see here that the input that was provided, which is the news article, was about how there was hefty falls in the stock market, which led to where 600,000 vehicles were sold in Japan, which led to the overall shares for the electronics giant Sony falling by about 1.7%. And this had a big impact on the Nikkei index, which eventually had a big impact on the S&P index as well. Now, the headline for this that the human labeler, the target output, the human labeler came up with was shares in Japanese automaker Mitsubishi Motors plunged 13.5%. Now, you can use the token level DEP score to see exactly which words the model was having a hard time with. So you can see here when I turn this on that specifically the model was having a hard time on words like automaker or Mitsubishi and the number 13.5%. And when what also happens is the model tells you about the other tokens it was considering. So when you hover on Mitsubishi, you can see that it's telling you that it probably should have been Sony instead. So it's almost again like an expert telling you how to fix things. And so I can quickly go and edit this target in Galileo and change this to say, Sony. And I could do this. My subject matter expert could do this, and it gets added to what we call an edits card, where you're basically improving the input data set, and you so that you can export and work with a better quality data set for the next run. The last thing I'm going to walk through is, as promised, I talked about how all of this was for the ground truth. How do you figure out if the ground truth is good or bad, whether it's using the automated clustering technology from Galileo, where you can start to see quick clusters, whether depth score is really, really high, or just using the just eyeballing and figuring out which clusters you want to inspect specifically, right? The second thing I want to talk about was the output. How do you know if the model's output is hallucinating or not? And that's where, amongst other metrics, the uncertainty score becomes really interesting. So if I look at the LLM uncertainty score here, this is a typical distribution where there's a long tail of really highly uncertain data points. So when I select this, I can see certain options showing up over here where you can quickly get a sense for, specifically when you click on the links, where the model was having a hard time in its generated output. And you can start to see that it's basically on this first name where it's literally struggling with coming up with the first name here. When it comes to numbers, it's struggling as well. If I look at the other outputs as well, again, the first name Steve is where it's struggling, and again the number is where it's struggling. The name is where it's struggling. So quickly, I can figure out that first names and ages numbers is where it's struggling a lot. So that's important for me to know so that I can fix the input that I'm working with next. And I can make sure that the model doesn't hallucinate on those, so it has more context from the data that is provided to it. So at a very high level, this is typically how you would want to go through an experimentation process and make sure that when you're doing this, you can keep track of all of this in one place over time. And then it's very important to compare all of these runs in across each other. But in order to do all of these things, again, just to go back to the whole point behind this workshop, super important to start thinking about the metrics that you're working with. It's very important to define those in the first place before you embark on the prompt engineering with RAG process or fine-tuning, or if you're doing both. So I'll stop there. I know we have about a few minutes remaining. Would love to get into any questions that people have.
Absolutely. And thank you so much, Vikram and Atindria. This has been great. I know there's a lot of questions in the chat. We only have time for a few, but I think I've summarized, a couple of the important ones. I think the first one is, can we use adherence to check for text in a large document? If we summarized multiple call transcripts, where can we point out from where the LLM made the context?
Maybe I can take a quick stab at that. So the short answer is yes. So irrespective of the size of the document, we basically detect adherence issues, if any. But then it can depend on how you're chunking the data. And essentially, we run adherence at a request level. So if you're chunking the data in a certain format, but are able to cohesively get together the full context in a single request, then most certainly yes. And as you saw in the slides, we're able to pinpoint, even if it's a large document, specific areas in the document where the model used that area or that chunk as a basis for reasoning, and whether or not it was logically correct or not.
Absolutely. All right, let's take the next question. How do you mitigate hallucinations in situations where you're streaming live output to the user and therefore don't have the full text to analyze beforehand?
Do you want to take a stab, Vikram?
Yeah, I was just thinking about this. So it sounds like it's a situation where you have it's a production application where you have the output from the model directly going to the user. This is where, there are two parts to this, in my opinion. Like, one is there's before you even deploy the model, right? It's almost like with software engineering when you're QCing, and you have to make sure that you're thinking about every single possible outcome before you even launch the model. That's where experimentation on the prompt engineering side, if you will, becomes really important to have all of those use cases and workflows mentioned. Even if you do that, as we know with applications, similarly with models as well, there things will go wrong with your when you're streaming live. And that's where, again, like having on real-time analytics and measurements with these metrics like our correctness score and adherence score becomes super important. So that you will be slightly reactive in those cases, but at least it helps in mitigating those kinds of situations from escalating further. And having effective alerts in those cases also helps quite a bit.
Yeah, just to add to that, I think in theory, of course, you can essentially take, your partial generation and, measure hallucinations, measure correctness. So in theory, it works. But if you think of like a practical system, you essentially want the entire completion to finish before you make a judgment call on whether something's hallucinated or not, for many reasons, including the fact that the answer might be in the last bit of the completion, or so yeah, essentially that. So that can lead to a lot of like false negatives or false positives. So if you are to design an eager system which is trying to measure these kind of metrics in real time, a better metric to measure in real time would be the uncertainty, because that gives you sort of a soft signal of how the models reacting, or how the model's getting confused as it's spitting tokens out. But if you want to measure hallucination, it is better practice to wait for the completion to finish and then make a call.
Which doesn't take too long.
Definitely. Okay, I think this is our last question for today. How reliable can you reproduce results? I've seen LLM is non-deterministic, even with temperature equals 0. How do you make sure metrics first is reliable if you can't always reproduce?
Yeah, I mean, to be honest, there is, like any other metric, there is a certain dependence on the reliability of the models themselves, uh, which is the reason why we've built the chain polling system in a way which is very modular, and it's very plug and play. So if you remember the box and arrows diagram, there's a couple of internal LLMs. In the default cases, they can be the source LLM themselves, but you can plug and play them out to use third-party models, which might be more powerful, might be less powerful. And also there's the internal, the chain of thought prompts, as well as the generation prompts, the complexity of which can determine the efficacy of the output. So there's all these knobs that you might have to tune. And you're right. I mean, these are all non-deterministic systems, so there's no reliable way to produce results. But that our experiments were done at scale and done across thousands and thousands of hallucination utterances across various tasks. And on aggregate, the results you saw was at 85% accuracy. So that's our job to, at least amortized, we can say that the metric sort of works.
Yeah, and then last thing I would add is like it is that is something that you notice as well, where the LLM output is pretty non-deterministic even when temperature is equal to 0. But that is why you need these kinds of guardrails in place constantly, because that's the power, the boon and bane of these LLMs. But I also would urge for people to start thinking about the whole having the multiple checks that we do for creating these metrics in place today, where there's a majority voting that automatically happens as a part of the creation of the LLM. The creation of the metrics output happens for exactly this reason, because behind the scenes we're basically asking it with the same API call, asking the same LLM 5 times, just to avoid this lack of stability issue and the lack of reliability issue.
Great. Well, thank you so much, Vikram and Atindria. This has been an amazing workshop. I'm sure everyone learned so much. So for anyone that's still here, thank you for coming. Please take the survey in the chat to have any feedback of how we should run our events in the future, what other topics you would love to hear, even from Galileo as well. And we hope to see you next time and keep learning. Take care, everyone. Bye.
Thank you.
Thank you.